From a simple apple falling from a tree to a planet orbiting a star, there are these invisible forces all around us basically running the show. In this explainer, we're going to pull back the curtain on the fundamental rules that make everything move. So let's just dive right in. Okay, so here's a weird one for you. A train, right? It's chugging along on a track, fighting friction the whole way. And then you've got a rocket just coasting through the total emptiness of space. What could they possibly have in common? Well, turns out they share a deep, fundamental connection that explains how they both get from point A to point B. That's right. Believe it or not, all of their motion, their entire behavior, can be predicted and described by one single, elegant principle. A rule that pretty much governs the entire universe. And that big, universal principle? It's really all about the relationship between a push or a pull and how something moves. Let's just call it the rule of push. Okay, so this is it. The big one. Newton's second law of motion. Now there's a fancy definition, but it all boils down to this iconic little equation. Force equals mass times acceleration. F equals m. This simple formula is literally the key to understanding, well, almost all motion. So let's break that down real quick. F is the force, that's the push or pull, and we measure it in newtons. M is the mass, which is basically how much stuff is in an object, measured in kilograms. And A is for acceleration, or how quickly an object's speed changes. These three things, they're basically joined at the hip. So, how do we actually put this powerful little formula to work in the real world? Let's take a look at how these three elements kind of dance together. The first, and honestly the most important step, is to figure out every single force that's acting on whatever you're looking at. To do that, we draw something called a free body diagram. So for this caravan here, we've got the engine pulling it forward, we have friction from the road and air trying to hold it back, we've got gravity pulling it straight down, and the ground itself pushing right back up. You gotta see all the players on the field. And this is where the magic happens. Once you've laid out all the forces, the math is actually pretty easy. First, we figure out the net force moving it forward. So we take the pulling force, 3,500 newtons, and subtract the friction, 500 newtons, which leaves us with 3,000. Then we just plug everything into our formula. We know the force is 3,000, and the mass is 1,000 kilograms. We just rearrange it to solve for A, the acceleration, and bam, we get 3 meters per second squared. It's as simple as that. Okay, so that was a nice, simple, straight line. But what happens when things get a little tilted? Let's check out a slightly trickier example to see how this law really holds up. Now check this out. For an object sitting on a slope, gravity is still doing its thing, pulling straight down toward the center of the Earth. But obviously, the object can't go through the slope, it can only move along it. So the real question is, how much of that gravity is actually making it slide? Well, this is where we do something called resolving the forces, which is just a fancy way of saying we use a little bit of geometry to break that downward pull of gravity into pieces. We figure out the part of gravity that's pulling parallel to the slope, which in this case is 386 newtons. And then it's the exact same game as before. We just apply F equals ma. 386 newtons of force divided by the 60 kilogram mass gives us an acceleration of 6.43 meters per second squared. See? Same law, you just have to be a little clever about which force you use. But there's this really fascinating twist to the whole story of forces. They never, ever act alone. And this brings us to Newton's third, and I think maybe his most mind-bending law of motion. You've probably heard this one before. For every action, there is an equal and opposite reaction. It's famous for a reason. It means forces always, always come in pairs. You just can't push on something without it pushing back on you with the exact same amount of force. It's a two-way street. And this is just a perfect example. A swimmer pushes backward on the pool wall, that's the action. The reaction is the wall pushing forward on the swimmer. Now that force from the wall is what actually makes her shoot forward. And here's the key part that trips people up. The forces are equal, sure, but they act on different objects. One force is on the wall, the other is on the swimmer. That's why they don't just cancel each other out. It's the exact same deal for a runner. To move forward, she has to push backward on the ground, and the ground, in reaction, pushes her forward. Seriously, every single step you take is a perfect little physics lesson on Newton's third law. And once you start looking for it, you see this principle absolutely everywhere. Rockets don't push off a launch pad to get into space, they push hot gas out behind them, and that gas pushes the rocket forward. Birds fly by pushing air down, and the air pushes them up. An octopus shoots water backward to jet itself forward. It's all just action and reaction. So we've got our rule of push, F equals ma, and our rule of pairs, action-reaction. Let's try and combine everything we've learned and tackle one last, kind of tricky scenario. All right, so here we have a professor pushing a cart that's loaded up with equipment. We've got all the numbers for the forces and the masses. But the question is very, very specific. How much force are her hands exerting directly on the cart itself? Okay, the secret to solving this is all about how we choose to define our system. First, if we look at the professor and the cart as one big group, her push is happening inside that system. But if we decide to only look at the cart as its own separate system, then her push suddenly becomes an external force acting on it. And since we figured out the acceleration for the whole group, we can now zoom in and use F equals ma to analyze just the cart. So we just take the mass of the cart and its stuff, multiply it by that acceleration we already found for the whole system, and we get our answer. The force that the professor is putting directly onto the cart is 53 newtons. So you might be asking, wait a minute, where did the rest of that big 150 Newton force go? And that's the crucial insight here. A huge chunk of that force was used just to accelerate the professor's own body. The force from the floor gets distributed across the entire system. It really shows you how important it is to be super clear about what you're analyzing. And this really just brings us right back to the heart of it all. This quote sums it up perfectly. Every single push, every pull, it's all part of this grand cosmic dance. Nothing in the universe ever acts alone. And that leaves us with one final thing to chew on. If every single action force has an equal and opposite reaction force, why don't they just cancel each other out all the time? How is it even possible for anything to move at all? It's a bit of a brain teaser, isn't it? Something to think about. Thanks for watching.